Welcome. Today's notes worksheet is entitled Using Derivatives to Maximize or Minimize. You've probably done a variety of application problems over the last couple of years dealing with what is called optimization, either trying to maximize a particular quantity or minimize a particular quantity. And in doing so, you've probably used the graphing calculator and the function on there to find that max or min. What we're going to do is try to find a mathematical way to go ahead and find a maximum on a particular graph or a minimum on a particular graph. So why don't we go ahead and start it out with the example one that I see on the board here. It says describe the instantaneous rate of change at each point. And I think what we're going to have to do, of course, is draw a graph in place here and then kind of analyze it. So if you get a chance, just go ahead and draw an arbitrary coordinate plane. And let's go ahead and throw a function in place. Doesn't have to be anything special. Just anything that passes the vertical line test should suffice. So something like that. And what I'm going to do is just pick 5 random points on this graph right here. And it would be great for you to kind of think about what would be the instantaneous rate of change at each point. So let's go ahead and put those points in. I'm going to put one right here. And I'm just going to call that point A. I'm not going to get all fancy with this one. And then how about right up there, I'm going to go ahead and call that point B. Right down here, let's go point C. Right here, everybody, this would be point D. And then how about right here would be point E. All right, so again, just 5 random points on the graph of this particular function. And what I'm after is a description of the instantaneous rate of change. So remember, of course, instantaneous rate of change is really coming from the concept of a derivative of the function. And the derivative of a function, of course, describes the slope of the tangent line for a particular point on the graph of the function. And so if I kind of look at this piece right here, I guess I would ask you, what would the slope of the tangent line look like here? So here's my tangent line, give or take, going through point A. See that in action. And I guess I would ask you this. I'll try to narrow it down for you. Do you think that would be a positive, negative, or 0 instantaneous rate of change? Well, based on the idea right here, I'm hoping you would agree that that tangent line looks to be inclining. And we know, of course, the slope of any inclining line is positive. So at point A, I think we would say, be comfortable saying at least, that the instantaneous rate of change is positive. I see one more point out of the remaining 4 where that would be the same case. And I'm hoping you would then say that point E has an instantaneous rate of change that would be considered positive. Something along those lines right there. Okay, let's keep it going. How about for, let's go this one actually. Let's do point C. So in this case, kind of coming down, it's a decreasing interval. And in this case, if I was to kind of think of the tangent line there, something like that, give or take, and you could see the tangent line would be declining in this case. And of course, a declining line has a negative slope. And so as a result, we could say that the instantaneous rate of change at point C would be negative. Now here's the key, everyone. What about B and what about D? So B resides at the local maximum. D resides at the local minimum. Describe the tangent line at the max and describe the tangent line at the min. Well, if I was to draw this in place and get a line to be tangent at that point to this curve, I think it would have to look just like this right here. I think there's the only way to pull it off, a perfectly horizontal tangent line. Same thing on D. At the minimum, the only way to draw the tangent line at that point is for it to be perfectly horizontal, something like that right there. And so as a result, if I look at those tangent lines at the max and min, the question is, what is the slope of a horizontal line? And the slope of a horizontal line is 0. And so as a result, now what we have is that the instantaneous rate of change right there at B and at D would be 0. And so let's start putting this together a little bit, and we'll try a couple examples. But very simply, here's what I have. Conclusion. A max or min for any function can definitely be found by determining, and let's get this other piece in play here, where the slope of the tangent line, of course, and when we talk about the slope of the tangent line, what we're talking about is, of course, the derivative. So where the derivative is, and there it is, everybody, where it is 0. And that's what we saw up here as you guys are writing that in just one more time. At that maximum, the slope of the tangent line is 0. So the derivative is 0. And right down here at the min, the tangent line is horizontal. The slope of that tangent line is going to be 0. And so what we're looking for is where the derivative is 0. And that's what we're going to be focused on for these few examples that we see. All right, that looks great. Let's continue then. So I'm going to start out really quite simple here with a quadratic function. And I do know that there is an easier way for coming up with what would be the minimum of this. As we all know, of course, a quadratic function forms a parabola on the coordinate plane. And we do know, of course, that the minimum essentially is the vertex. And you've learned ways to go ahead and find the vertex algebraically that do not need the concept of calculus. That's fine. But what I would like to do is at least see this all in action so we can get a good sense of it before the functions get a little harder. So let's go ahead and give this a try. It says, example 2, let f of x equal x squared plus 4x minus 6. And what we're going to do first, of course, is find the derivative of the function. And then we're going to go ahead and utilize the derivative to find what would be either the max or the min. And I think I gave it away that this would be a min. So let's give it a try. Let's get just a little practice dealing with finding a derivative again. So the limit is h goes to 0. And then f of x plus h, so this would be x plus h squared. And then plus 4 times x plus h minus 6. And then minus, just be a little careful when we do our f of x, of course. Get that in parentheses on the back end there. And we all know that's over h. All right, so that is our first step, and that's looking pretty good. You've had a lot of experience with this right now, and it should be coming a little more automatic for you. Let's take that limit as h goes to 0. And I've got x squared, 2xh, and h squared. Of course, when I go ahead and expand this piece right here, let's remove those parentheses. I have 4x, 4h, minus 6. Looking good. And again, let's remove the parentheses on the back end as well. So minus x squared, minus 4x, and of course, how about a plus 6 there? Looking great. Okay, and all of that's over h. Let's continue this process. Let's go ahead and cancel out some terms. X squareds, say goodbye. 4x's, they're gone. 6's, of course, crossed out as well. Looking pretty good. And so I'm going to go ahead and rewrite just to make sure you guys are doing this as well. Again, you can definitely work ahead of me if you'd like. I have 2xh plus h squared plus 4h. And all over h is doing it. It's good. You can definitely see the top. We're going to go ahead and factor out an h at this time. So let's go ahead and do that piece. So I've got the limit as h goes to 0. Pull it out, and I've got 2x plus the h plus the 4. And again, looking great. H's are going to cancel at this stage, which is exactly what we wanted. And I'm going to do this in 2 steps. If you'd like to shortchange it just a touch from here, you're more than welcome to. But at this stage, this is what I have. And now we go ahead and take that limit as h goes to 0. That's the key. And once we take that limit as h goes to 0, we let h be 0, and there's my derivative. So let's go ahead and put this piece in action. I'm going to go ahead and put that as f prime of x equals, and that looks awesome. Okay, so we found the derivative. Absolutely perfect. Now the conclusion that we came up with at the top of the page is that very simply, a max or a min is found when, again, the slope of the tangent line is 0, or when the derivative is 0. Both mean the same thing. So I'm going to go ahead and try to write this out just to be as clear as possible for these steps. But very simply, number one is set the derivative to 0. We want to know where the derivative is 0. So set the derivative to 0 and solve for x. Again, that's the conclusion we made. The derivative is 0 at a max or a min. So let's find out where that happens. So I do this right here, guys. All I do is I make the derivative equivalent to 0, and I solve for x. So f prime of x is 0. Now, guys, this shouldn't be too bad. Let's bring the 4 over. Let's divide by the 2, and I get x is negative 2. So at an x value of negative 2, there is going to be a minimum here. And again, kind of determined that it was going to be a min because this is a parabola opening up. All right, now here's where we just have to be a touch careful. Obviously, when we're talking about a max or a min, we're talking about an ordered pair on the coordinate plane. It has an x and it has a y. Now this is where you have to be careful. Plug that x value into the function. That's the key. I'm going to go ahead and underline this. Please do so as well. So into that function to find the y coordinate. Not the derivative, guys. If you put this in the derivative, obviously you're just going to get 0 out of it. That's not what we're after. So we want to know where the function is maximized or minimized. And in order to do that, we know this is the x value that's going to produce the max or min. So it goes back into the function, and we go ahead and solve. So this is step 1 right here. Now, guys, step 2 is saying, all right, that's my x value. And so it goes back in, and I do negative 2 squared plus 4 times negative 2 and minus 6. And if you go ahead and do this on the calculator, it looks like I get a 4 minus the 8 minus the 6. And so I'm seeing that as negative 10. All right, so that's the key, everyone. In order to find the true max or min, what you have to do is take that negative 2 and it goes into the function. That's the key. And now, guys, we've got it. As a matter of fact, that's pretty much all there is to it. Negative 2, negative 10, and there is your minimum. Again, it is a parabola opening up, and so the vertex is a min. And there you go. Looks great. So that's how we're going to use the derivative there. Again, in days past, you would have to graph this. Well, not for a quadratic, but for other ones, you'd have to graph it and go ahead and use the function on the calculator, which is great, of course. Obviously, we want to use the technology. But what I'm just trying to show is a mathematical way to pull some of that stuff off. Okay, let's continue. Let's go ahead and up the ante a little bit here. And let's do example 3, which is now a cubic function. So let's see what we have going on here. It says let f of x equal, and I've got a pretty long cubic on that, find the local max and the local min if this is the derivative. So I was kind on this one, everyone. It looks like I gave you the derivative. What do you say we kind of box that up, because we're going to go ahead and use that. And I guess the concept here is that we want to go ahead and find the maximum and the minimum. And I'll show you what this looks like momentarily when all's said and done, but let's see how the math plays out first. So guys, it's very simply a 2-step process. If we're going to maximize or minimize any particular function, we set the derivative to 0. So we take that and we set the derivative to 0. Now I'll give you 2 options on this. I'll play out both ways and then see what you think. In this case, this looks like a nice quadratic here that we should be able to solve. I sort of see this as being able to factor a little, and I'm going to go ahead and do that if it's all right with you. Let's see how this math plays out by me taking out a 6 here, and I get this. There you go. That's kind of nice. I could have divided by 6 as well. That would have been just fine, because this is going to be irrelevant when we solve for x. But basically, I end up getting, it looks like x minus 4 and x minus 1. And so as a result, I'm hoping you see when I take this and set it to 0, I of course get x equals 4. When I set this equal to 0, it looks like I get x equals 1. That's not bad at all. So that's great. So there are two x values that are going to produce either a max or a min for this particular function. An x value of 4 is going to produce either a max or a min, and an x value of 1 is going to produce either a max or a min. Now there's only one way to kind of tell. Let's put them back in. Remember guys, where do we put them back in? The function. We put them back into the function, and we'll see which is the highest value, which is the lowest value, and we can kind of go from there. So let's give it a try. So two things we need to do here. Number one, put 4 back into the function. Sorry for being redundant, but it's the one mistake I've seen with these over the years. Don't put it into the derivative, put it into the function. So let's get that going. I'm going to try to do 2 of these almost simultaneously here. So I've got that, 24 times 4, and plus the 19. And that's going to be equal to something which we'll get momentarily. Now guys, obviously, what we want to do is take that 1 and repeat the process. So I'm going to do the same thing, 2 times 1 cubed minus 15 times 1 squared, 24 times the 1, and of course plus the 19. And this, producing the max or min, is going to be some number here, which I will get momentarily. So I'm ready to calculate. Please do it with me. And let's see where it leads. So here's what I have. 2 times 4 cubed, and then minus 15 times the 4, plus 24 times the 4, and plus the 19. Hopefully I have that all typed in correctly. I think I'm going to have to go back and look at that momentarily there. So minus 15, I see my mistake. Let's go ahead and fix that right up here. There we go. Square didn't come through. So let me get that going. There we go. So much better. And so as a result, it looks like when I put 4 into the equation, I end up getting 3 as an output. Input 4, output 3. Now, still not sure if that is a max or a min. I think what we're going to have to do is kind of put this in place and see what the 1 would produce, and then we can make our determination from there. So here we go. Let's just put the 1 in. I don't mind doing it. Please do it with me, though. And then 15 times the 1 squared. Here we go. 24 times the 1. And how about we add the 19? And again, hopefully I typed it in correctly. I think I got it this time. And I'm getting a 30 when all's said and done. All right, so at this stage, guys, we have this. We have 4 comma 3, and we have 1 comma 30. Now, obviously, guys, if I look at those two, those are 2 points on the graph of the function. One happens to be a max, and one happens to be a min. And, you know, make the determination, guys, which is which. Well, obviously, the larger number has to be the max, so there is the high point right there. The 1 produces the 30. And obviously, the lower one there is the minimum. And so it would look something like that. And just real quick, I mean, this looks great at this stage. A cubic function we should be very comfortable with. In this stage, it kind of looks like that, give or take. And I will tell you, this point right here is going to be 1 comma 30. There is your maximum. And this one right over here happens to be 4 comma 3. So you could put a lot of the things that we've talked about over the course of the entire year into perspective. But basically what we did is just found a mathematical way to maximize and minimize a particular function. All right, really looks quite nice. The beauty of this one, of course, was I gave you the derivative. That made it quite easier, didn't it? What do you say we do one application here, and then we'll start to round this out a little bit. So example 4. An open-top box is to be constructed from an 8-foot by 10-foot rectangular piece of sheet metal by cutting square corners and folding up the flaps. Write a function for the volume, V, of the box in terms of x, and x would represent the amount cut from each corner. So I can pretty much guarantee you have seen this scenario before, probably in a couple different contexts. We're going to talk about it in terms of maximizing momentarily, and then we'll kind of go for it. So just to rehash what this looks like, we have this piece right here. So this would be 8 by 10. So let's go ahead and label that appropriately. And again, if you haven't seen this before, that's okay. Don't worry about it. But this is a very common problem for the levels of math that you guys are working on here. So chances are you've run into it before. All right, so we have the 8 by 10. Now what we're going to do is cut out identical corners. Let's cut out the squares here. Here we go, something like this. And the dimensions of those squares can vary. So that's going to be our variable, x by x. Okay, and basically the volume of the box that can be produced is dependent on those squares, on the dimensions of the squares, on the x, so to speak. So I guess what we want to do is kind of look at this, and again, excuse my poor drawing. That's what happens when you're artistically challenged, but you get something like this, give or take. If I cut out those square corners, you end up getting something along those lines right here. And guys, you're going to just have to use your imagination a little bit. Once those squares are cut and they're out, we fold up the resulting flaps. So 1, 2, 3, and 4. So try to picture those 4 flaps being folded up, and they meet together and they form an open top box. And of course, if it's an open top box, the volume of that box would very simply be length times width times height. All right. And again, potentially you've seen this before. What is the length of the box? What is the width of the box? And what is the height of the box? Well, they are all expressions in terms of x. And so what we're going to do is write the volume of the box in terms of x. All right. Absolutely great. Well, let's put it together. I'll try to use both diagrams here. So we were 10 all the way across on that length, but then I cut out x from this corner, and I also cut out x from this corner in order to get this piece right here, which would be the length of the box. So I started at 10, and I took away an x from each corner, so I took away 2 x's. So this expression right here would be 10 minus 2x. All right, wonderful. Now I go back, and the width of my original piece of sheet metal was 8, and I took away x from here, took away x from here, and so same premise, everyone. It looks like this would be the width of the box, and it looks like I started at 8 and took away 2 x's. Okay, great. Now, remember the height of the box would be the resulting flap, essentially, and picture the flap as a result. Bring that on up, and I hope you're okay with me saying that the height of the box is actually equivalent to this length right here, which we already sort of ascribed as x. And so there you go. I think that's your height. There's your x right here. Now, if for whatever reason you don't see one of those particular 3 dimensions, please let me know about it, and I can walk you through in a little more detail. But regardless, we've got ourselves a nice function right here. Depending on how x changes, it's going to affect the volume of the open top box. Excellent. Now this, if we were to multiply it out, and you are not, it is not necessary to do so, it would be a cubic function. And so let's move now to part B. And here's the nice thing about this. That cubic function that we created for part A, I found the derivative. Here it is right here, everyone. There's your derivative of this function right here. So one more time, this is the derivative of this. So I found it for you. That was nice of me. We're going to utilize it, though, and see if we can maximize the volume of the box. So again, this is what's called an optimization problem. An infinite number of ways to construct this box right here based on x. We're going to try to find the value of x that would maximize the volume of the box. Okay, so let's do it. So I have v prime of x right here. This is the derivative of the function from part A. Now what we're going to do is find the maximum volume of the box and what are its dimensions. All right, well, let's get it going. First thing we do, like we've done a couple times already, we set that derivative to 0. So there we have it. Now it's good news, bad news. Bad news first. This actually does not factor. So it does not benefit us to try to factor this. I'll give you that ahead of time. Just doesn't help. So what we're going to do is plan B. We know how to solve quadratic equations. And of course, that's how we work with this. We go through our methods of solving quadratic equations. You've done these so many times. You've factored. You've completed squares before. But you know what? I think it's time for us to go ahead and let the calculator do at least a little work on this. And so what you're going to do for me, guys, is go to your program and let's do the quadratic formula. So hit program, quadratic formula, hit enter, and hit enter one more time. And let's let the calculator get us the values of x here. So A is 12. There it is right there, of course. B is negative 72. Okay, that looks good. C is positive 80. And I have two values for x that make this equation true. So two values of x that make the derivative 0. And I'm going to go ahead and just round to a couple decimal places here. We could probably do a little better, but that's all right. So I got about 4.53, and I also got about 1.48. Nope, sorry, 1.47. Let's go try to round appropriately there. So let's do about 1.47 on that. Okay, now this is absolutely perfect. Here's the only thing. I need to determine which is going to produce the maximum. So do I want the x value to be 4.53 to produce the best volume possible? Or do I want the x value to be 1.47 to produce the best x value possible? Well, there's only one way to find out, guys. We have to put both those values back in where? The function. So they go back into the function, and one of them is going to be the best value. One would be the minimum, which obviously we don't want to minimize. We want to maximize here. So it's sort of a fixed scenario right here, and we want to produce the most space inside the box as possible. So let's go ahead and do it. That is equal to something, and that is equal to something. They go back into the function. So I've got this, the 10 minus 2 times x, 8 minus 2 times x, times the x. I don't mind taking the lead on this, so I'm going to go ahead and do that right up here. And I'm just going to let the calculator do the work. So again, I've got 10 minus 2 times 4.53, okay, and then 8 minus 2 times 4.53, and then times one more time there. It looks like 4.53, give or take. Close them. Ooh, that's interesting. I've got a negative volume, so that tells us pretty much right away. I think I saw something like this. This definitely is the minimum on that, right? I mean, it simply can't work. Can't have a negative volume, so that would be the minimum on the graph of the function, which I guess is irrelevant for us. So I think that leads me to believe that this, everybody, here we go, that one right there is going to produce the maximum. Let's go get it. So 10 minus 2 times, and I'm going to go for about 1.47-ish, and then 8 minus 2 times, same deal, of course, everybody, and then 1.47. There we go. And we get our maximum volume of about, I think I saw about 52.51, and this would be cubic feet. And guys, that's your max. Absolutely great. So it did say, find the maximum volume of the box, which we just did. So out of the infinite number of ways to construct this box, we would want x to be equal to about 1.47 feet, which would produce a volume of just over 52.5 cubic feet, and that's the best you can do. That's the optimal volume for that box right there. Wonderful. There's one last piece, and then we'll wrap this on up. It does say what are the dimensions. So this is obviously the volume, and the volume comes from the length and the width and the height. I'll just go ahead and tell you that what you need to do is exactly what I did initially, is just put the 1.47 in here, get the length, put the 1.47 in here, get the width, and put 1.47 in right there, and you get the height. So I have this on my paper. Why don't I just kind of give it to you? And I've got mine rounded, but it's basically these would be the dimensions. So I've got about 7.06 feet by 5.06 feet by 1.47. So again, all I did is put my 1.47 in here, and then in here, and then in here, and you end up getting these three numbers. And so lo and behold, let's see, I've got these as all of it. Oh, that looks very, very cool. So if you need the quadratic formula program, just touch base with me. I'd be happy to link you up. It just literally takes 5 seconds. It's not a problem at all. Cool. Why don't we stop that one right there? Thanks for listening, of course, and let me know if you have any questions on it. Pretty cool math, I should say.